All right. Okay. So last week, last Thursday, we introduced the topic and we did one simple problem. All right. Basic on dimensional analysis. Now let's further expand that. Okay. Okay. We further expand that and to more complicated problems. All right, involving more parameters. All right, and then we also discuss the common. All right, common dimensionless group. Okay, and if you can got time, we do example. If not, we'll do example tomorrow. All right. So, basically, for any problem, all right, there's some function here. There are certain things you can control. All right, I put on the right hand side. Those are your input. Okay, and then this side is your output. Is that okay? So, example, if you want to do well in the exam, so the output may be your marks, all right, final grade, etc. Then your input may be number of hours per week or something like that. Okay. Unit contents. Okay. Some units easier than others. Alright. So could be depend on your question paper. Alright. Normally, okay. Normally, final question paper is the most dependent because that one, alright, normally contributes the most. Final exam, questions, all right, assignments, anything else? All right. So this one, in this particular case, some of them are a bit subjective in the measurements. All right. So hard to quantify. Okay. In other words, when you say like easy or hard exam questions, you know, it may be easy to some, it may be hard to others. Some people can understand it, some people cannot. All right, but never mind. Okay, for engineering problems, all right, for the technical ones, the not so technical ones may not work out so easily. All right, but basically, if you have the same input here, all right, same input. Alright, you expect the same output. Okay? This is not some random process. Okay? So in other words, alright, in a ideal situation, if you and your friend did everything the same, alright, approximately the same abilities, and you put in the same amount of work and so on, maybe you should get the same mark. I don't know whether that happens or not. Alright? But for engineering problem, if your inputs are the same, all right, same, you expect the outputs to be the same. Is that okay? Right or not? Inputs, in other words, you do an experiment, you measure flow rate, you measure forces on the thing and so on. All right, if you have the same input, all right, you expect the same output. Is that okay? All right, or not? All right, so for the dimensionless groups, all right, what we are doing now is we reduce the number of parameters by using the dimensional analysis. If the same input, we also expect the same output. Okay, I'll describe that a little bit more. I'll highlight that again. But let's say, okay, our problem, all right, okay, this is some flow problem. Okay, so say maybe, all right, some liquid here. Okay, there's an impeller. All right, maybe you're concerned about certain things. Okay, maybe the tank has baffles. All right, and maybe you're concerned on forces. your concern forces on baffles, all right, and maybe pressure at strategic locations. Okay, maybe the pressure too high, pressure too low might damage your equipment, and so on. Okay, so output here, maybe force, maybe pressure. The baffles are normally for mixing tank, all right. You wouldn't have just a cylinder with an impeller inside. From the top view, you have this one, you have your impeller here. You normally have baffles here, like strips of metal or walls are sticking out. So instead of the flow able to just go around like this, it's forced to go around the baffles. That helps you enhance your mixing. Okay? Alright? So could be forces, could be pressure, could be certain fluctuations. Alright, within the tank, maybe some unsteadiness. So could be frequency. Frequency of those fluctuations. Okay or not? Alright, the input could be density of the fluid. Forces on baffles. Baffles. Pressure, pressure at strategic locations. Alright. Alright, maybe certain points you have you want to you concern pressure go too high, pressure go too low, got damage or whatever. Just example. Alright. So this is typically, alright, certain outputs. Alright, forces, pressure, frequency. Okay. Certain inputs, rho, maybe the velocity. Alright, you could actually in this case you could choose two velocities. You can either choose maybe the blade tip velocity, which is omega r. Okay, or you could choose just omega. All right, that was the same. I choose omega. I choose velocity. Tomorrow I choose omega. Okay, today I choose velocity. Maybe the diameter. All right, diameter. But maybe your dimensions here got the small d. This big D could be the what diameter? Yeah, so this one could be blade. This one could be tank, or the other way around, doesn't matter. Okay. So there are two diameters, two scales. Okay. What else could there be? The fluid properties, let's say viscosity. All right. There could be gravity. It's an input. All right, because this one is this is air, this is liquid. All right, if you have any surface waves, okay, the gravity force is what's restoring it. So if your gravity is higher or lower, all right, that will have an effect. All right, some of you might think, how to change gravity? Okay, you could maybe repeat the experiment on a different planet. All right, or you could actually enhance gravity through like a centrifuge chamber. All right, you can actually, it's not so easy to decrease gravity, but it's quite easy to increase gravity. All right, so in certain cases, you put this whole thing in a rotating chamber. All right, you can actually increase the effective gravity here. All right, okay, if you want to do so. Okay, so you can, but for now, we just put gravity as an input. All right, we can control, not easily, but could be controlled. Okay. The fluid properties like density and mu, you can control. I can change the fluid. Maybe instead of water, you can change to oil or other things. All right. So we have control on that one. Anything else? Rho, V, mu, G. Anything else? Let me cheat and see. Anything? Make sure I got all the. I think. Oh, I forgot. C is speed of sound. All right. If you don't know by now, speed of sound also depend on the fluid property. All right, certain fluids the speed of sound is lower, certain fluids the speed of sound is higher. The material, like if it's a solid, normally the speed of sound is very higher. Okay, so that's also a property of the fluid now. All right, so rho, mu, and C are fluid properties. Okay, big D, small d is the property of the geometry. Big G, well, that's environmental properties. Property of the environment, which we input our where we want to do an experiment. Okay, so this, it can be more, all right? Okay, it can be more, like temperature, thermal conductivity, all right, and so on. Okay, so but we only stop for there now. All right, and output also could be more also. Okay, could be a lot of other output, but for now we'll stop at this. This is as complex as you need to get for now. All right, for this unit, but later on, when you do other units, okay, they will talk about temperature and so on. Okay, but this again, this is the basic analysis. All right, they can form a dimensionless group on temperature, on thermal conductivity, on other conductivity, and so on. Okay, what's that called? Huh? I can't remember. Some number or something. Okay. All right. There are a lot more. But they're not in this unit, so don't worry now. Huh? Reynolds number will be here. Don't worry. Okay. You got mu here. You get Reynolds number. All right. Thermal conductivity K normally, and then other properties. You'll come out with other new dimensionless groups. Okay. All right. For now, just these ones and these ones, forces and frequency. Okay, that's possibly our output. All right. Forces, pressure drop, pressure rise, frequency, and so on. Okay. Normally, any questions so far? This is some generic problem. It could be the impeller problem, could be another problem also. Never mind. Okay, some generic problem. What I'm saying is, all right, just now at the start, if I repeat the exact same conditions, all right, I put in all the same parameters into the problem, I should expect to be able to repeat it. Okay, if I print out the cooking recipe, I took it with me to some other country and I repeat it. All right, hopefully I can repeat exactly all the inputs. I should get back the same output, right? With new rig and everything. Is that okay? Yeah. All right. Maybe I used to work somewhere, then I defected, went up north or went down south, and then I rebuilt the thing. I should be able to do it again. Okay. Sometimes you go from north to south. Sometimes you go from south to north. I don't know. Not you. All right, east to west, west to east. Some people do go back. Okay, you can't understand why. Yeah. Anyway, okay. So as long as you repeat it, it should work. All right. So we'll do the dimensional analysis now, and then I'll further elaborate on that topic. Okay. So the normal, like what we did yesterday, the normal culprits is rho, V, and D. All right. That is our repeating. Okay. So we obviously have 3. All right. If you don't count all these ones, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 variables, 10 parameters. Okay. I didn't show it here. Parameters. All right, but there's 3 basic dimensions in all these ones. All right, they're M, L, and T. I didn't show it out, but you can show. All right, there's no temperature, so there's no temperature variable. So in each one of these, there's only 3 basic dimensions that can be expressed in M, L, and T. Normally that's the case for this unit. Rarely you might get 2. I don't think that you can do problems with just one variable. All right, so rarely you'll get 2, usually you get 3, you'll never get 4, not in this unit, but other times you might get. Okay? So we expect 7 groups. Okay? So we expect a group, you take out these 3, okay, you take out these 3, count how many left. There should be 7 left, isn't it? Okay, no? 1, 2, don't count the dot and all the words that are written. 1, 2, 3 on the left, 4, 5, 6, 7 on the right. Okay? Alright. So let's go and form that group. Okay? Alright now. So we'll form those 7 groups. Okay? If I'm going too fast, let me know. If I'm going too slow, also let me know. Maybe you, alright? Okay? So we start with force. Force. Alright? Force divide by rho to the A. Rho to the A. V to the B. D to the C. Alright? That's one dimensionless group. Okay, that's why I call one dimensionless group. Alright? Okay. What's the dimensions of force? Mass. Alright. Multiplied by acceleration. L over T squared. Okay, that's the dimension for force. F equals ma. Alright. Density, well, that's m over L cubed to the power A. Velocity to the length over time to the power B. And length to the power C. Okay or not? Alright, this is exactly what we did last week. Alright, is equal to, you can tidy it up, m to the power of 1 minus A. Okay. T to the power of minus 2. Minus becomes plus B. Alright? Because the denominator becomes a numerator. Alright, L, you will get 1 minus 3A plus B plus C. Alright? We want this group to be dimensionless, so M to the naught, T to the naught, L to the naught. Is that okay? Sorry, minus become plus. Yeah, so mistake. Okay, so minus 3A, minus becomes plus 3A minus B minus C. Okay, so 1 minus A equals to 0. Therefore, A equals to 1. You do the T. Minus 2 plus B equals to 0. B equals to 2. L. 1 plus 3A minus B minus C is equal to 0. So 1 plus 3. Therefore, 1 plus 3 minus B minus 2 minus C equals to 0. C is equal to what? C equals to 2. Is that right? Right or not? Half 2. 1 plus 3, 4. 4 minus 2 is 2. 2. C is 2. Okay? So the dimensionless group here, alright, is force over rho V squared D squared. Alright? Sometimes, okay, this is the pi number 1. Sometimes they put force over half rho V squared A. Okay? Because, why? If I add half here, does it make dimensionless or non-dimensionless? Still dimensionless, isn't it? Okay? So sometimes, just for convenience sake, you can put a half, but I'll tell you why. Alright? And this diameter, alright, in some cases, the problem may involve a diameter or length scale. Sometimes the problem involves an area, so it's easier to just put A. Okay? Both also have the same, still dimensionless, isn't it? Okay, so the problem, easier to express in A than express in A. Easier to express in diameter square, express in diameter square. It's problem dependent. Okay or not? Alright, don't panic. Alright, both also correct. Alright? If you do exam, you do left hand side, you get full marks. You do right hand side, you get full marks also. Okay, both correct one. Alright? And this one is called a force coefficient. Alright? example, if this force was a drag force, then you call it a drag force, e.g. drag force coefficient, or lift force coefficient, right? Or any other, depending what force that is. Okay? So it's a dimensionless group. Alright, not? Does it mean anything or not? Alright. Does it mean anything or not? Alright? Actually, it has a physical meaning. Alright? Okay? What it is, half rho v squared A is like your, looks like, okay, doesn't have to exactly like, but looks like, this looks like your fluid momentum, isn't it? Half rho v squared, alright? M dot V, isn't it? M dot V per unit area. M dot V is what? M dot V is equal to rho A V multiplied by V. Alright? Rho V squared A. Alright? Okay, it looks a bit like your fluid momentum, isn't it? Okay? So, and the half, well, normally the kinetic energy, there's a half one, isn't it? Alright? Half rho v squared in your kinetic energy term, in your Bernoulli equation. Alright, that's where the half comes from. Okay, but half or no half, it doesn't matter. Alright, this is like, so it's like your external, your force divided by the fluid, by the momentum force. Okay, not? So if it's like, so it's your force over fluid momentum force. Okay, this force again could be what force, whatever it is, lift or drag and so on, etc. Okay, so it's like a force. This is exactly a force ratio. All right. So this output, all right, this number, okay, you get a number like 1 or 2 or 3 or whatever, or 0.5 or something. This number is actually a ratio, approximate ratio of your fluid forces and your output forces are lift or drag or so on. Okay, so it actually has a physical meaning on. They're not just just for fun. These numbers actually have a meaning. Okay, so each time I go to the other ones, I'll also write that. Okay, so the other one, okay, so that one say pressure over rho. Actually, I know already, but you want me? I'll do it for you lah. Okay, one more example. Pressure over rho to the A, V to the B, D to the C. This A, B, and C is different from the earlier one. Alright? Force is actually, pressure is actually force M L over T squared 1 over L squared. Force per unit area. Okay, this is force area. Alright? Rho is M over L cubed to the A, VL over time to the B, and DL to the C is equal to, okay, M to the power of 1 minus A, T, L to power 1 plus 3A, this one cancel out, L to power minus 1, okay, L minus 3A, plus 3A, minus B, minus C, and T to the power of, yeah, so 1 minus 2, that's why it's minus 1, okay, T to the power of minus 2, minus becomes plus B. equals to m to the naught, L to the naught, T to the naught. Is that okay or not? Alright, so for the M equation, 1 minus A equals 0, A equals to 1. L equation, okay, alright, L equation is minus, no, let's do the T equation first. T equation, B is equal to 2. L equation, C is equal to 0. Okay or not? Alright. Y 0, you can try putting up. 1 minus 1 plus 3 is 2. 2 minus 2 is 0. So 0 minus C equals 0, C is 0. Alright? You can do yourself. Okay? But I knew already lah. Because pressure, you divide by area. So here, if you the top you divide by area, the bottom must divide by area also. So you'll get pressure over half rho V squared. Okay? Alright, so not surprising, the Bernoulli equation, P plus half rho V squared plus rho GH equals constant. Alright, so that's why they choose to use a half here, because this is your P and this is your, if they both can add together means they are dimension, they should be the same dimensions. Alright, and this is your pressure coefficient. Alright, so if you measure pressure at some point and you want to turn it to a coefficient, it's like this. Okay, and it's basically ratio of dynamic to static pressure. Alright, wrong. Okay, static to dynamic. Okay, this is your static pressure and this is your dynamic pressure, so it's just a ratio of the pressure ratio. Okay, so far? Alright, okay. Any questions? Alright. Okay. Anyone confused? Anyone want to ask why we are doing this or anything like that? Okay. I'll come to the why soon lah. Alright. Okay, the last on the input side, F has a frequency, the dimensions of, okay, so we want to form one, rho to the A, V to the B, D to the C. Alright, this one has the dimensions of 1 over time. Okay, it's a frequency. Maybe something's oscillating. Rho is what? M over L cube to the A. V is L over T to the B. D is L to the C. Okay? M to power minus A. Show 0, yeah. Okay? P, L to power of minus 3A, plus 3A minus B minus C. T to power 1 plus B. Okay? Minus B minus B become plus B. Okay? Equals 0. So from here, repeat? Oh, sorry, negative 1 plus B. Okay, so minus A is equal to 0, A equals to 0. This is your M. L minus 3A, no, don't do L first, do T first. Okay, P first, B is equal to 1. So L, 3A minus B minus C is equal to 0. To 0, L to 0, P to. Okay, then what you got? A is 0, B, therefore C is equal to minus B is equal to minus 1. So we put it back. Alright, the dimensions will be F, roll to the north, so nothing. V, B, B, V, and C is minus 1, so T. A, D. Okay? Sometimes they call F D over V, sometimes they call F L over V. Same. Alright? The D or the L is the length scale involved. Right? The principal length scale involved. Okay? Alright, so it depends on the problem. Okay? This one is normally called the Strouhal number. Alright, Strouhal is, some of these numbers are named after, appear very often, and they are named after, so abbreviation normally ST. Alright, they are named after famous scientists or mathematicians or engineers in the past. Okay, and this one appears very often, that's why they give it a name. Okay, a bit more fancy name. And this one, alright, is basically F is the frequency. Alright, and you want to call it V over L. It's actually these are F V over L. Alright, and this one is actually time scale, flow time scale. Alright, so it's a ratio of the what's happening, alright, what you're measuring over this velocity of L is like your flow time scale. Right, this is your characteristic velocity, L is your length scale of the problem. So this V over L will give you some idea of what sort of time to expect in the type of problem you have. Okay? Does that make sense? Alright, so it's a time scale ratio. Okay? So these are our output so far. I've done 3. Okay? Shall we do the next one? You all now quite familiar how to do it already, huh? Okay? So let's say you do for D. Actually, this one I know already lah. Okay? You can go ahead and do it on your own to test. But I'm sure small d over big D is dimensionless. Alright? Small d dimension length, big T dimension length. Alright? So this is more like a length ratio. Alright? If you want to do the same experiment, obviously you must scale what this states is. Alright? If you want to do the same experiment, you must scale appropriately lah. Alright? Among other things, minimum is if your blade is always half the size of your tank, alright? You want to do a scale experiment, the blade should be half the size of the tank. Alright? Cannot scale differently. In other words, one experiment, alright, you scale, you do one blade is 30% of the tank, and the other one is 70% of the tank. It's a different experiment. Is that okay? So if you want to do experiment, a scale model testing, you must have the right scale size. Okay, next one, what? Huh? Mu. I think mu we done already, huh? Alright, we did this on Thursday. You want, you can try again. You'll get the same result. This one is normally called the Reynolds number. Alright. Okay, so it's named after the famous engineer Osborne Reynolds that did the famous pipe flow experiment, which we'll talk about later. Okay, he's the first one who did it sometime in the 18th century. University of Manchester. His experimental rig still preserved there in the university if you want to go there. Okay, and see it. Okay, but it's quite far away. But Malaysia Airlines got direct flight to London. So from London to there, I think it's only 2 to 3 hour car ride. Can take train or plane if you like. Okay. Alright. So this one is, again, these creatures up here is like your flow inertia. Okay. And this creature down here is like your viscous effects. Okay. So when your RE is very big, all right, RE big, all right, flow momentum dominates. Okay, when the RE is small, viscous effects dominate. Okay? Is that alright? What I mean here is, okay, so for when viscous effects dominate, okay, the viscous forces tend to it's like what we studied, alright? Okay, when viscous forces dominate, they tend to smoothen out, they tend to have a viscous effect, like a glue, alright, makes like things become very sticky kind of flow, alright? Doesn't matter what size the flow is, it can be sticky big flow, it can be sticky small flow, alright? But it's sticky flow. If momentum dominates, then it's a fast moving, not the opposite of sticky, alright? Very easy moving kind of flow. Is that alright? Okay, that's really what the Reynolds number represents. Alright? Later on in the unit, we will talk about, for specific problems, there are specific transitions. The flow goes into different flow regimes based on particular Reynolds numbers. Alright, but those are all for a particular problem. Alright, those are more specialized. The general one is, okay, flow momentum dominates, tend to be more turbulent, more less sticky. The other one is very viscous, very sticky flow. Okay, you want to write it that way. We'll talk about it for particular problems, but this is actually what it represents. Okay, and you want to look up the history of Osborne-Reynolds, you can type on internet and read, you know. Maybe sometimes you got difficulty sleeping, then you can read. Okay, you can read his life story, what he did, and all that. Okay, what other one? G and C. Okay, G over rho to the A, B to the, let me cheat the C. G on top, bottom, no, below. Alright, rho to the A, V to the B, D to the C over G. Okay? Actually, both doesn't matter. You invert also can. Just that if I invert, then it's actually it's not Reynolds number, it's the invert of the Reynolds number. Okay? Because Reynolds number got name. Alright? But either way, this way, that way, square everything, square root everything, all also same. Alright? If it's dimensionless, you square it, you have to power 3, to power half, to power 1/3, all same. Okay, not? It's still dimensionless. The other thing doesn't matter. That's why some ask me why I put 1 here. Okay, for the top fella. If I put 2 also can. Put 3 also can. In other words, I put 2 here. Or I don't like, I put 3 here. Okay? All the result is this one 3 over 3. Okay? Okay, so the choice of choosing up, down, left, right, putting number there, 1, 2, 3, all doesn't matter. As long as the end product is dimensionless, I cannot take any marks away from you. Okay? I mean to one dimensionless. To form dimensionless groups. Alright? So you want dimensionless. Okay. Alright, no, the other one is different. Last Thursday I said something, we don't want to form a dimensionless groups. That is, if you take just these 3 repeating variables, we don't want to form a dimensionless group. Alright? They shouldn't be able to form. But that 3 plus your other one, that will form a dimensionless group. Okay? The choice of that one is not, if you choose the 3 that will form dimensionless group, there tend to be, that's the only dimensionless group they will be forming. Okay? Alright, so this one, rho, let's see. Maybe you forgot how to do already, because we have been doing shortcut. M over L cube to the A, L over T to the B, L to the C, over L over T squared to the 1. Okay? Alright. So, M to the A, L to the minus 3A plus B plus C, and T, A, minus 1. T to the minus B, plus 2. Okay or not? Alright? And then you say that's m to the naught, l to the naught, t to the naught. So a is 0, b is 2, and c is what? Minus 3a plus b plus c minus 1 equals to 0. 3a, that one's gone. b, 2 plus c minus 1 equals to 0. C equals to minus 1. Okay? So the group, it should be, rho is not v to the b, v squared d over gd, something like that. Okay? That one, they don't like to write it that way. Alright, you just square root the whole thing. Alright, we should, okay. Alright, I write v over gd square root. Okay? If the v squared over gd is dimensionless, if I square root the top and square root the bottom, should still be dimensionless, isn't it? Okay? So they like to write it that way. Or sometimes v over square root of gl, depending what the problem is, whether it's the diameter or length or something, it's a problem. And this one is normally called Strouhal number. Okay? Again, it's actually your, okay, v over square root of d divided by square root of g. Okay? Alright? Again, it's your okay, it has meaning. Alright? Bottom here is like the gravity force. Here is like, again, your inertia, fluid forces. Maybe some don't like call it force, but you can call it force or effect, fluid effects. Okay? So this one, again, your velocity and your length scale, so it's your flow parameters. Alright? And G is your effect of gravity, so how the ratio. Okay? If you have, okay? Is this the last one? No, I think the one more. Okay? If you have, alright, in other words, no, sorry, this is not Strouhal number, sorry. It's called Froude number. Alright? Okay? Froude number, I talked earlier already. Okay, Froude number, Froude is a famous mathematician, also quite a while back, maybe a bit earlier. Alright? And that name, the number name after him. Okay? If you have a Froude number very high, means G effect small. Alright? Means normally the Froude number is a factor when you have a free surface because you have waves. Okay? What's generating the waves is something, but what's trying to restore the waves, alright, is your gravity. Okay? So if your G effect is small, then you have a small restoration effect. Your waves can continue, they won't, it could be quite choppy. Okay? If your Froude number is the other way, okay, G effect is big, alright, the G will tend to restore. Okay? Restoration force. Big to calm waves. Okay? So Froude number normally to do with waves, but it could do with other things as well. Normally free surface effect. Because each of them have a different density. Gravity is the what is separating them. Right? If no gravity, then your water and your air will be mixing around. So gravity is the one separating them and the one that will try to restore. Okay, final one, I put C. Alright, C is the speed of sound. C over rho to the A, V to the B, D to the C. I can skip this one lah. Here. Alright, I can guess this is the answer already. Alright, dimensionless or not? Alright, this speed of sound has a dimension of speed. Velocity also has a dimension of speed, so dimensionless. Okay, but if you don't believe, homework, again, maybe you find it difficult to sleep or nothing to do at the bus stand or something, you can try it out. Okay, So, alright, and this one is called the Mach number. Alright, also named after a famous scientist. Alright, okay, C. Alright, this is actually ratio of flow. Actually, the other way around, huh? V over C. Ratio of flow speed over sound speed. Okay, and it has a great effect. Alright, quiet please. We don't talk so much about compressible flow in this unit, but for high speed flow, where your velocity, where V over C is maybe more than 0.2 or 0.3, then compressible effects start becoming significant. Alright, so that's when your flow speed and your sound speed are comparable, or maybe sometimes your flow speed higher than your sound speed. Okay, that has a big effect on the flow. Alright, that's why if you look, some aeroplanes have a rounded nose, and some aeroplanes have a pointy nose. Correct or not? Alright, these aeroplanes with a rounded nose meant to travel at subsonic speed. These aeroplanes with a pointy nose are designed to travel at supersonic speed. Okay, that's why a lot less drag if you have a pointy nose when you're doing so. So rockets and all that have a pointy nose. Alright, you guys watch The Dictator. Okay, he's insistent that the rocket had a rounded or pointy, I don't know. Okay, okay, alright, and it has effect. Okay, let me sum it up. Alright, so for our problem, okay, some function. Alright, here is say force over half rho v squared d squared. We have pressure over half rho v squared, and we have one more frequency, f l over d. Alright, okay, and here we had rho vd over mu. We had we had small d over big D. We had, what else can I remember? I had V over square root of GL or GD. Okay, we had C over big D. Okay, C over big D. Alright, but others we don't care. Alright, so this is as complicated as the problem you can get. Alright, okay, so if the exam come out question with repeating with rho v and some length scale appearing on the in a parameter list, okay, then actually, well, you can skip the steps and jump straight to the dimensionless group. If you cannot remember the dimensionless group, it's in your formula sheet. Okay? So unlikely exam will be that easy. Okay? The formulas are here. Right? Pressure coefficient, drag coefficient, lift coefficient, Strouhal number, Froude number, Reynolds number. Okay, that's the only numbers you need to worry about. If it's a non-standard problem, alright, maybe the parameter list doesn't have velocity. Alright, normally right? V over C, sorry. Alright, settle down please. Last statement here. Okay, quiet please. If the velocity, if the repeating, if you cannot choose rho v and d as your repeating variables, then you actually have to choose follow the rule, choose 3 and then do them, and then you might get non-standard groups. Never mind. Alright, so there's the possibility. Alright, and final statement, this one most important one. We will do examples next tomorrow. Okay, alright, quiet please. If these inputs are the same, alright, doesn't mean you have now doesn't mean you have to recreate everything identical. All right? Okay? All right? In other words, you have to make the same diameter, same working fluid, same gravity and all that. It can be different. All right? But as long as all the input parameters are the same, the input dimensionless groups are the same, all right, then we expect the same output, dimensionless groups. Okay? Does that make sense? All right? The earlier one made sense, eh? If you repeated your experiment, put in all the same parameters, you expect the same output. Here, this theory here takes you one step further, and this is how you apply this one. In either both scaling between model and full scale, or scaling between all the tables and charts that for standard problem already printed in your textbook and your particular problem. For all that scaling, as long as your input parameters are the same, okay, depending. In this case, it's 3-dimensional parameters, but there could be less, there could be more, right? All right. As long as those are the same, we can expect the same output dimensionless group. Is that clear? All right. In other words, this phi, you put in the same things here, we expect the same. This one to be the same. Okay? We'll do an example tomorrow. We put in the same one, and then we see whether we expect the same one out here. Okay? See you tomorrow. We're outside. Alright? Let me see. Those expecting my signature, please wait outside, because I think next class wants to come in. Okay.